Welcome back, everybody. Hopefully, you all did really well on your test last week. This week, we're going to switch gears just a bit. We've spent a lot of time talking about motion in the first chapter, and we talked a bit about energy in the last chapter. And we're going to still talk about energy some, but we're going to talk about energy in a slightly different way. And while doing that, we're going to talk about the way that things behave, as you've seen in the videos previous to this one. But there are a few problems that I want to show you that'll be in your practice problems that I want to make sure that you have some examples of. So that's what we're going to do here. These are much easier than the ones that you're used to from the previous sections. So don't worry if it seems easier, than the others. It should be easier. First of all, we did talk about temperature this week. Remember, there are essentially three different temperature scales. The Fahrenheit scale is used just by us here in the United States and in a few other islands. I think Belize might use it as well. I think I saw that. Okay, Celsius is used pretty much everywhere else. Okay, this is also the measurement that's generally used in science when they don't use the Kelvin measurements. It kind of depends. Fahrenheit, we are very different using that. It is a very different temperature scale compared to the others. Okay, water freezes at 32 degrees Fahrenheit and boils at 212. But for Celsius, water freezes at 0 and boils at 100 degrees. Okay, Celsius was set to be this way. It was set so that 0 would be when water froze, 100 degrees would be when it boiled, and each degree in between is split up evenly. If you want to convert between the two temperature scales, right, we can use these conversion equations here, and we'll use these in just a minute in an example. Now, if we use the kinetic theory of gases that we talked about this week, the idea that the temperature of a gas is equal to the average kinetic energy of the particles that are moving around, we can assign a value of 0 to the point where all motion, all kinetic energy stops. We call that point absolute 0. And then we can essentially measure the temperature up from that point, right? That's the bottom point. There is no upper limit to temperature, but there is a lower limit. There's only so far that you can go down, and that would be absolute 0. I think your textbook refers to this as the absolute temperature, but it's also the Kelvin temperature scale. The temperatures in Kelvin don't use degrees, they're just Kelvin. But they have the same range as a Celsius degree. So when you want to switch between Kelvin and Celsius, you just add or subtract 273. It actually should be 273.15, but I think your textbook rounds it. So let's convert this temperature of 13 degrees in Celsius to Fahrenheit. So remember that the temperature in Fahrenheit is going to be 9/5 times the temperature in Celsius plus 32. And so what we're going to do is just plug in 13. And then you're going to use your calculator to solve this. 9/5, which is really just 1.8 times 13, will give you 23.4 plus 32. And you get a temperature of 55.4 degrees Fahrenheit. Those of you who want to try my experiment this week where you switch everything and start using Celsius, 13 degrees Celsius is when it's a little chilly outside, 55 degrees. Let's try another one. We're going to go the opposite way this time. We want to convert a temperature of 107 degrees Fahrenheit to Celsius. Now that's pretty hot if it was 107 outside. The temperature in Celsius is equal to 5/9 times the temperature in Fahrenheit minus 32. It's important that you subtract first here and then multiply. 107 minus 32 will give you 75. And then when you multiply, you get 41.7 degrees Celsius. If it gets close to 40 degrees Celsius, it's pretty hot outside. Between 30 and 40, it's really warm. It's essentially summertime. 20 and 30 is more like spring or fall. 0 to 10 is essentially winter, or anything below that. Depends on where you guys live. You guys are much more north than me here in Mississippi. We don't see below zero temperatures all that often. It does happen. So in addition to being able to switch between different temperature scales, we also talked this week about the specific heat of materials, right, and water in general, and how that specific heat is different depending on the material. And that is essentially just a measure of how easy it is to heat something up or to cool it down. And so metals tend to have very low specific heats because they're easy to warm up or cool down. That's why you cook things in metal. Water has a really high specific heat, as you see here. And we base our measurements off of water because of its high specific heat. And we can introduce this new unit here called calories, which a calorie is just the amount of energy required. 1 calorie is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. And that amount of energy is equal to 4.186 joules. If we know the specific heat of water or whatever the substance is, we can determine how much heat we would need to raise its temperature. And so this equation you have here is just giving you the amount of heat energy that you would need to raise the temperature of some mass of an object by some amount, right? And then C just represents the specific heat capacity. And so this value would come from a table, or it would come from some other information that was given to you. It is specific to the material. So in the next example, we'll use this equation, and then in the following example, we'll calculate the specific heat for something. Be careful with the units here. You can sometimes see joules per gram. You can sometimes see joules per kilogram. The numbers will change in that case. So just be aware of that. We're going to use joules per gram for our examples. We want to know how many kilojoules of heat are needed to raise the temperature of 346 grams of water from 4 degrees to 100 degrees. As we're heating up some water for a cup of coffee, and that reminds me to take a sip of my own. It says to round to the nearest integer. Integers are just positive or negative whole numbers, right? So no decimals here. We're just going to round to a whole number when we're done, but a whole number of kilojoules. So we're going to use our quantity of heat equation, and that's the mass times C times the change in temperature. The change in temperature is the final temperature minus the initial temperature. But you can see that it's going from 4 to 100 degrees, so this would be 96 degrees Celsius. The mass is 346 grams. Because we're going to use this value for C, the specific heat of water, and we have grams here, we're going to use the mass in grams. So 346 grams. The specific heat, 4.18, I always forget the last number, 186 joules per gram per degree Celsius times 96 degrees Celsius. And I wrote the units in here just so you can see how they cancel out. And that's why it's important to use them. And you want to make sure that you have the masses in the right units. If you multiply all these values together, you will get 139,042 joules. And that J looks a little strange at the end. It's like 5. Joules, or 139 kilojoules, the nearest integer of kilojoules. This would be 139.042 joules, and then you round. Relatively simple. You just have to be careful with those units. Make sure you're using the right units. That should be a decimal point. So now we want to find the specific heat of wood, right? So we're told that 60 kilojoules of heat are added to a 1.6 kilogram piece of wood, whose temperature then rose from 19 degrees to 41 degrees. What was the specific heat? Well, we can use the quantity of heat equation and just rearrange it to solve for C, right? And to do that, we're essentially going to divide by M times delta T. And I'm showing you this because you can use this for any problem where you're trying to find C. It is the amount of energy, the quantity of heat that is required, divided by the mass times the change in temperature. 60 kilojoules is 60,000 joules. The mass is 1.6 kilograms, or 1,600 grams. And the change in temperature, 41 minus 19 is 22. And so that's 60,000 divided by 1,600 times 22. So you can write that part down. 35,200. And then if we divide those two, 1.70 joules per gram per degree C. So this is the specific heat for wood. Notice it is much less than the specific heat for water. Right? Water is going to have a higher specific heat than most things. Not everything, but most things. Finally, we talked a little bit about density this week. We're going to pick up and talk more about density and pressure problems next week as we go on into the second half of the chapter. But I did want to show you one problem with density. There's a couple in your practice problems this week. Recall that the density of an object is just the mass divided by its volume, okay, how much space it takes up. And so the mass is how much matter it's made out of. The volume is how much space it takes up. And that'll give you a measure of the density, how dense something is, how compact the mass is. And we use rho, the Greek letter rho looks kind of like a P, to represent the density. So let's try one last problem with this. We have a room that's 10 meters long, 7 meters wide, and 5 meters high. What's the mass of the air that it contains if the density of air is 1.3 kilograms per meter cubed? Well, we need the volume of the room. For a square, volume is just length times width times height. And so that's 10 meters times 7 meters times 5 meters. And if we multiply all of those, that's 350 meters cubed. And so this is our volume. Remember that the density rho is equal to the mass divided by the volume. Again, we can rearrange this to solve for the mass by just essentially cross multiplying. But the mass is the density times the volume. Wrong Greek letter. Or 1.3 kilograms per meter cubed. I don't know why I have so much trouble with this. Times the volume, which is 350 meters cubed. The cubic meters will cancel, and you're going to be left with units of kilograms. And when we multiply 350 times 1.3, you'll find that the air in the room has a mass of 455 kilograms. Notice this is non-zero. Doesn't feel like there's that much, but there is. And this is something that you'll see in the videos that we watched this week as well. The air pressure in any room is generally a lot greater than you realize because you're so used to living in it, it doesn't really, you don't really see what it does until you see how it changes things. And so that last video in the demonstrations this week, hopefully you saw that with the drum when they emptied out all the air, and it's a bit exciting. And we're going to continue this discussion of temperature and heat and thermal energy on into next week. If you have any questions, please let me know. Next week is spring break, so it'll carry on for 2 weeks. We'll kind of break it up as we go along. And I believe I promised your project last time, but I will get it to you guys very soon. And so there'll be some more info on that coming. If you have any questions or if there's any way I can help you with any of these problems, please let me know. And I will see you guys next week.